Thank you for joining me on Profiles in Discovery. Tonight it is a pleasure to welcome John Singer, University Professor Emeritus, who has revolutionized our understanding of cells, the building blocks of which we are all composed. Biological membranes are crucial to the function of cells, receiving signals from the environment and regulating the flow of materials in and out of cells. Among many other contributions, John has dramatically changed our understanding of biological membranes. Welcome, John.
Glad to be here.
In your career, you have switched fields several times, in fact, many times, and you have distinguished a linear career in which one moves forward with a steady, extended analysis of perhaps a single set of problems, to a jumping career in which one moves from one set of problems to another. What have been the benefits and perhaps some of the difficulties of switching fields in this way?
Most biological fields start out in a very confined way. We know very little about them and at a particular time, and people rush in to try to augment the information in them. And there are innumerable such fields. Mm-hmm. Generally, when a faculty member comes in as a young man, he picks one of these that he has some feeling for and proceeds to work in this field for a considerable number of years. Now, as time goes on, each of these fields expands its knowledge based on what
people jump in
as well. And the individual himself broadens out a little bit and acquires some of this knowledge, of course, and uses it for his own work. In many cases, people start in a field at an early age and then stay with it for a very long time.
This would be the linear model.
That's the linear model, and do so very successfully. One thinks of Arthur Kornberg, DNA metabolism and things like that. And so it's a common way to do it, and it's perfectly fine. Others of us have a different personality and like to be a little bit more varied in their total appreciation of biology. So I started out as a physical biochemist, which involved knowing a lot about protein structure and so on. But that's still a viable field. And at the time I started, it was not too well known, but it's become very complicated since in its expansion. But at a certain point, I stopped being that interested in it and became interested from being a chemist to being a biologist, which by that time I really felt an urge to do. But I didn't know any biology then.
How do you prepare for a jump of this kind from one field to another?
Well, I had been a postdoc with Linus Pauling before I took a faculty job at Yale. But as a postdoc, I had a lot to do with the immediately adjacent biology department. Pauling was in the chemistry department. So I observed a great deal of what was going on in biology, and it fascinated me. So I thought that was a general area I wanted to go into. But to pick a specific domain of this kind, I started out on the antigen-antibody reaction, the basis of immunity, to try to understand how the proteins involved saw each other specifically, recognized each other. And that was a very active field for many years. But about 1965, when I was back at UCSD, the secret of how specificity is achieved in this process was solved. And it seemed to me, not by me, but by other people, and it seemed to me it was time to move on. Although I could have stayed in that field profitably.
By my count, you've jumped, I think, 6 or possibly even more times during your career. It's quite like remarkable.
But there's a condition, I mean, it's not arbitrary. The condition is that you have to have some idea of what you're going to bring to a new field. Conversely, a lot of fields are impregnated by ideas that come from outside, from people who are not experts in the particular field in question. And they bring with them techniques or information or insights that people within the field do not possess. And I always looked to try to do that kind of thing when I made a jump. I mean, I didn't arbitrarily make a jump. So when I got into that next jump, which was cell membranes, I applied my understanding of protein physical chemistry to the problem, because at the time, and I got in, it's hard to believe how primitive a state
the good old days
it was in the early 1960s. It was understood that the proteins contain molecules called lipids and proteins, but nothing was known about the nature of the proteins. None of the proteins of membranes had been isolated or identified or in any way characterized, except they were somehow appreciated to be different from the ordinary water-soluble proteins that are in our blood, serum, and other body fluids. And there had to be some reason why certain membrane proteins were associated with membranes. And we came up with a notion of derived from protein physical chemistry that everybody knew in the protein field, that if you had certain amino acids which are called hydrophobic, meaning that they tend to sequester away from water contact, that these might be concentrated in the interior portions of the lipid membrane.
Again, away from the water on either side,
and that these long stretches of so-called hydrophobic amino acid residues would be located in the membrane, connected to ordinary stretches of amino acid sequence on either side. So we proposed that membrane proteins were so-called amphipathic, having two natures, and that they span the membrane.
John, your model, the fluid mosaic model of the membrane with the proteins floating in the lipid sea, if you will, is now in all the textbooks. It's really dramatically altered the way we think about biological membranes. But let me ask about the changing field of biology as we've seen it over the decades. Do you think it's now perhaps more difficult to make jumps from one field to another because of the increasing complexity of biology? Will it be possible in the future to continue doing this, to jump?
That's very hard to say. I think part of it depends on the generation of new fields. There's not a static number of fields out there, but as progress in the sciences develop, new fields arise. The borderline between genetics and behavior, and other areas which are completely underdeveloped at the present time, are areas that are ripe for outsiders coming in. These are now subjects that are in the province of psychologists and other social scientists with very little input from classical biology, in particular genetics. And that's certain to change. The introduction of really fundamental genetics into behavior is a coming thing.
Yes.
So there are areas that are, in a sense, played out already. I mean, only in the sense that they're so well developed and have become so complicated that the issue is there of collecting the complications and understanding how to integrate all that. So a lot of advance has to be made in learning how to deal with very complicated systems, where at the beginning that same problem was so simple that it was only a question really of finding specific things of interest, individual things of interest. I mean, one thinks of muscle, for example, muscle action. I mean, at the beginning, the introduction of the idea that there was actin and myosin present as the fundamental proteins of muscle was the breakthrough that opened up a whole new development. But now we know hundreds of proteins that are very functionally important in the action of muscle. We know about neuromuscular junctions and things like that. So that whole problem area has become enormously more complex, but integrating that complexity is now the sine qua non of muscle physiology. So it's a matter of new fields developing that have the same quality of a low level of information, and jumping in with some idea from the outside as to how to augment that information.
You've done that repeatedly, John, and it's just been wonderful to watch here at UCSD. Let me ask, as you look at this development of science, and in particular biology, how do you think the challenges of this complexity to which you're just referring have changed the character of the institutional support for it and the institutional advance of science, the university in particular? How has that changed?
Well, I think the problem, if I take it a step back, is one that the scientists themselves have to face. That is, I've already partially referred to that in previous remark, but speaking more generally, biology is like one of the other natural sciences. It's just been, particularly molecular biology, has been a much more recent development. But if you look at physics or you look at chemistry, they have likewise experienced this growth from a very small amount of information and a few ideas and so on. They've grown into being very complex structures. And chemistry in particular, which in my old times,
your old field,
it used to be dominated by organic chemistry and certain things like electrolytes and so on. Chemistry has completely changed its character it's grown very complicated, and to find new areas in chemistry is extremely rare. So now nanotubes and things like that, which are kind of really oddball accoutrements of chemical science, have acquired a lot of interest. Mainly, I think, because there's not a hell of a lot else that chemists...
Well, perhaps chemistry is branching out, looking for the interfaces that you mentioned.
It's looking for interfaces. Yes, chemistry has certainly found one interface in biology, and is pursuing that. But what's going to happen to biology in time is a very similar set of developments, I think. That is, biology happens to, on the one hand, be much more complicated than any of the other sciences. So there's never going to be an end of things to do. It's just whether they're going to be really useful to do. I mean, you know, if you have 20 million species of flora and fauna, how many of those 20 million are you going to understand from A to Z in order to forward the nature of science? Certainly not all 20 million.
Well, I think the tendency will be, as you have done, John, to focus on understanding the fundamental principles, and that can perhaps be achieved by a more selective approach.
Well, that certainly will be the case, but eventually, like any other field of science, biology is going to get very complicated. We don't appreciate that quite yet because it's still such a young subject and there's so much left to do. But in some time, it's going to be so intricate that it will be a matter of integrating knowledge that's accumulated rather than finding the sort of basic knowledge that begins a subject, and the character of the thing is going to change. One of the problems with it is that the interest of the research person, who's I mean, the field may be expanding, but a person is an entity with certain limits on what he can encompass, he and she can encompass. The faculty member is going to become narrower in his pursuits, in his scientific research, rather than broader. And I think this is a very critical element in not only development of science, but in the development of the whole university.
John, you have noted on many occasions that the university, with a capital U here, really is the prime source of intellectual activity in the nation, with this double purpose, as you've emphasized, of discovery and enlightenment, the teaching, the transfer, the communication function. And I take your point here, as we tend to get more narrowly driven, this achievement of this double purpose becomes significantly greater. But I want to turn to your book. I brought a copy with me here, The Splendid Feast of Reason, a wonderful title. And want to ask you a little bit about this, because this, I think, is a powerful book, and in it you use science with a broad brush here, but particularly biology, as an example of the human mind to use rational thought in all of its activities. And I want to ask how, here in 2003, how do you see the future for rational thought? Will, on the one hand, perhaps we expand our use of rational thought as science and public life merge, the arts merge to a greater extent, or will this narrowness that we are concerned about, will that discourage the expansion of rational thought?
Well, Well, it's a very serious problem. First of all, I should mention this book has achieved the New York Times best non-seller list.
Not for long, John, not for long.
But it's a serious problem. I think what it entails is that the way our teaching program is organized, with a whole series of specific fragmented courses in any particular subject area. I mean, I've suggested that there will ultimately be an English course on British poetry from August 1934 to September 1935, and if we keep this kind of thing up.
Yes.
The problem becomes that the narrowness of the faculty members' research activities that is pressed on the faculty member is not a matter of really of choice, but is a matter of the directions in which the science is taking him or her. Confines their outlook so much, and the busyness, which is always increasing, confines them, so that they have less and less general interests in the community of scholars. And this is not a biology problem alone by any means. This is a problem in every one of the disciplines, because every one of the disciplines goes through the same evolution that we've been talking about for biological fields. On top of that, the integrated information at the top is so dense and complicated that only an expert in it is really in a position to understand it. The real problem for the student, though, is not focusing on one such development or another, but somehow integrating all this knowledge that he's been taught and that is available, so that one benefits by all this complexity instead of suffering from it. And one suffers from it if one gets a heavy dose of, say, biology, but is not going to go into biology in the future. How does what he learns in biology relate to what he's been doing in other disciplines?
Yes.
And for that, I think we do need a new culture in the university. There has to be, at the highest levels, a decision that some kind of mechanisms of integration have to be introduced into the educational system at the undergraduate level that don't exist at the present time.
John, you've offered for many years a course that is aimed at addressing this problem, and it's been tremendously successful, although, of course, limited in scope.
It's been a very small course. If you're looking at that now, it was a course designed for honors, an honors course for seniors in Revelle. That is, after they finished their curriculum, they would at the end be capable of taking this if they elected to do so.
In Revelle College.
In Revelle College.
Yes.
So it only had 16 students, but it covered an enormous variety of subjects, which involved science, but also politics, religion, the character of the human being as affected by technology. Actually, it was a course mostly based on technology rather than science, but because they're really, science and technology, in my view, are quite different enterprises. That's often thought not to be the case, that one is simply the outgrowth of the other, the technology from the science. But I don't believe that. I think in principle, technology being the application of science allows for a decision to be made at some point whether to apply the technology, whether to apply the scientific information to develop a piece of technology or not.
Yes.
As we have with human cloning, for example.
Yes.
There are people who feel that it's inevitable, no matter what we do, that human cloning will ultimately occur. Maybe not the next 10 years, maybe longer. But that means that if that were true, then science and technology would be linked in a way that was inseparable. So I think one of the problems we have to think about, and students should be thinking about, is how the scientific knowledge that we obtain, which is for the purpose of understanding the universe and man and what they're like, not for the purpose of manipulating the universe or man. That's technology. And one should make a clean cut, as much as possible, work at making a clean cut discrimination between these. That's a part of this course. And the relationship between science and religion and technology and politics, for example, those are areas that are not covered in conventional courses that I know about. They're really a mixture of humanities, social sciences, and the sciences. And my feeling is that there ought to be a considerable number of courses given at the later stages in an educational career, senior courses, of this character.
Tying things together.
Tying things together and making some kind of coherence out of the whole.
John, our time is all too short, and it's always so stimulating to talk with you and about any one of a range of topics. Your legacy, not only for UCSD, but for the country, both at the level of discovery, scientific discovery, and at the level of rational thought and communication, is impressive. It's been a great pleasure to have this opportunity to meet with you and discuss these topics. Thank you for joining us this evening on Profiles in Discovery.